Okay, we back to this exercise, and then for the last class I already teach you how solving these problems consider the material is the water. So the similar ideas, if we change the container's material inside, the B we change it to the air. So roughly we know the air, the composition is compressed with the nitrogen and the oxygens, but with the different percentage portions. So we know that we have the air, most of the composed with the nitrogen and the oxygens. So what's the molar mass? The molar mass, we know that we have 14 for the nitrogens, but we should multiply the 2. And then we know that the totally we have the 80% is composed of the airs for the nitrogens, and the oxygen is 16, and also we have the 2 O, and the composition percentage of the air is the 20%. Okay, so we try to recalculate the molar mass for the air. So you can use your calculator to compute the molar mass in here. For me, my answer is the 28.8, and also it's the gram per mole. And we only change the material. We didn't change the molecules numbers. So we actually keep the same mole. It's 0.166 and 10 minus 17 mole. So I can recalculate the mass in containers if the material is air. So again, I multiply the molar mass by the mole. So here the molar mass changed to the 28.8 G per mole, and multiply the mole number 0.166 and 1017 mole. So again, we can calculate how weight in the tank of the air. So that you can check your answer by yourself, and I just try to calculate in my site. So this is 4.7 A1 and 10 minus 17 G, and I convert it to the kilogram. So this is equal to 10 minus 20 kilogram. Okay, so right now we didn't know how density of the air. So I can provide you under the room condition, the raw air is around 1.2 kilograms per meter cubic. So we have the raw densities of the air. So we still can calculate how volumes of the tank. So the volumes will equal to the mass divided density. Okay, so right now the mass is the 4.7A1 and 10 minus 20 kilograms, and we need to divide the density is 1.2 and the kilograms per meter cubic. Okay, again we should cancel out some unit we don't need. So we don't have the kilogram and cancel out, and we have the final volumes will equal to again, use your calculator to compute. The true answers is the 3.984 and multiply the 10 power of minus 20 powers. And the unit right now is the meter cubic. So the answer required to the unit is the length of the cubit. So we should take the cubit root again and try to calculate the length. Okay, so you should use your calculator to compute the final answers. So in my side, I check the number around the 3.41 and the 10 minus 7 meter. Okay, so this is my answers for the material of the air. But you can find out a little bit difference for the answers compared to the values shown on the right corner upper. That's because different conditions we may apply the different density. Because we know that the density should be changed with a different temperature. Okay, so but a little bit difference is fine. It's just we just try to practice the idea for the continuous assumptions. Okay, so how can we decide the final volumes? So because based on our calculations, we just calculate the theoretical values. But usually theoretical cannot directly apply in real case. So most safeties, we will multiply the 100 times to our computer's answers. So even though we know that previous slide we compute the answer around this number, right? But we will multiply the 100 times for these values. Okay, so for our answer, we make the conclusion the cubit of the length should be larger than 3.1 10 minus 6 power meter. So this is for the liquid water at the room conditions. But if for the air and at the room conditions, we will suggest the cubit volume should be larger than 3.4 and 10 minus 5 powers meter. Okay, so this is very simple ideas, just based on the continuous assumptions, and how can we decide the container size to satisfy the continuous assumptions. If your container size is quite smaller, it cannot directly apply to measure the material physical properties. Okay, so the next topic is the units. As I mentioned, also you can go back to see the previous exercise. If we didn't know the units of the physical properties, we cannot figure out the questions answers. Okay, so for me, most important thing is the units. So in this slide, we show some physical property related to the mass, force, and density. That's the three primary properties we'll use in our class. And then the table just summarizes some important parameters: the length, speed, and the mass, density, and the force. And with the different symbol, you should keep in mind the symbol, because in this textbook we usually use the symbol L represent the length, V indicate the velocity, and the M is the mass, and Rho is the density, F is the force. And the different physical properties we have the different dimensionals. So the L and the LT and the M divided LT, L's cubit, and the NL divided T square. And there are some very important unit conversions I highlight by the red rectangle here. Okay, so if you don't want to remember everything shown on the table, at least you should keep in mind some highlight unit conversion here. Okay, I think you cannot remember everything shown on the table, but at least you should keep in mind some highlight unit conversion I show in here. So right now I can show you some important unit conversion step by step. So usually we know that the one FT will equal to 12 inch. And we know that 1 FT is equal to 0.3048 meter. Okay, so you should keep it in mind. And then how different the meter, usually we call that, for this unit, we call that this is a SI standard unit, right? And also we can call that is the metric unit. Okay, so usually the Chinese we say that the 公制. And if I change to the FT, that indicates we can call that is the English unit, or we can say that is an imperial unit, and we will say that is the 英制. So sometimes we just make some unit conversions. It's just based on the different units. And so you should remember some primary units for different physical properties. Okay? And then we know that the 1 kilogram will equal to the 2.205, and we call that the bond mass, the bond mass. So we will use the LBM. It's indicated the bond mass, the bond mass. And in other words, we know that the 1 bond mass will equal to 0.4535 kilograms. Okay, this is a very important unit conversions because when I'm doing the weighting trainings on gym, right? On gym, the machines sometimes they show different numbers on machines. So if you didn't know the unit, maybe later you can see the 10, but you didn't know the 10 kilogram or 10 pound. It's totally different, right? Around the half weight if you have a different the unit. Okay, so and I know that the 1 slug will equal to the 32.1. Oh, sorry, no, there's no space. So the 1 slug is equal to the 32.17 pound mass. So for the mass unit here, we should keep in mind some important units is the kg, pound mass, and the slug. Slug is not we cannot see in our life, not the very useful unit in Taiwan, but sometimes in engineering they will use the slug to represent the weight of the material. Okay, and then we know that the some density here is related to the liquid, right? The waters. And we know that the water density, if we convert to the imperial unit, will equal to the 32.43. Okay, but the density is fine because if I can convert the kg to pound mass, and I can convert the meter to FT. So you only keep in mind one version. It's enough. Because you know how to convert the kg, and then you know how to convert the meter. So don't worry, you just keep one version, and then you can convert it by yourself. If you cannot remember the value accurate. Okay, so in other case, we know that the 1 bomb is a 1 bomb force. So now it's not the bomb mass. How different they are? It's because the 1 bomb force, the meaning is equal to 1 bomb mass and multiply 1 gravity. Okay, the difference very important. 1 bomb force is equal to 1 bomb mass multiply 1 gravity. And then we know that how large of the 1 gravity, we always remember is equal to a 9.81, right? And the unit is the meter per second square. So for me, I can convert directly for the meter to ft, because I know 1 ft is equal to 0.3048 meter. So in here, I know that the 9.81, the meter, how can I convert it to ft? I can divide it the 0.3048, and the unit will change to the ft. And I keep the second square. So you can use your calculator to compute. Finally, I know the 1G will equal to the 9.81 divided 0.048. And it's around the 32.18. And the unit is ft divided the second square. And then I can put this number, go back to here. So this is the 1 bomb mass multiply 1G will equal to the 32.18 ft divided the second square. So I summarize the 1 bomb force in here. I know the 1 bomb force will equal to the 32.18 bomb mass multiply ft divided the second square. And you can see a little different compared to the number shown here. It's fine, because the gravity, maybe we use the different number. Here, the gravity. Okay, maybe some people use the 9.8, not include the 9.81. Okay, and because we know that the bomb mass multiply ft divided the second square, and then we still can convert the unit. When we convert the unit, we can convert the bomb mass to what? We can convert bomb mass to kilogram, right? And we can know how 1 bomb force equal to how many newtons. Okay, so I can rewrite. I know the 1 bomb force will equal to the 1 bomb mass, right? Multiply the 1 gravity. But I know the 1 gravity is equal to the 9.81 meter per second. So if I would like to have the newtons for the force, I should convert the bomb mass to the kg, right? Because the kg multiplied the meter per second is equal to the newton. Okay, so I know the 1 bomb mass will equal to the 0.4535 kilogram. So I can convert the number here is 0.4535 kilogram multiply the 9.81 meter per second square. And you can use your calculator to compute the Newton answers here. So it will equal to the 4.448 Newton. Okay. So for me, I only keep in mind for the length is how ft converts the meter. I will keep in mind. And the second, the mass, I will keep in mind the bomb mass converted to kilogram, or 1 kilogram converted to the bomb mass. At least I keep in mind 2 conversions units. And then I can recalculate everything in here. Because all of the force dimensional or the density dimensional, that related to the length and the mass. And the mass and the length here. And we always keep the second don't change. Because the second didn't change between the SI unit or the imperial unit. Okay? So when you repeatedly calculate by yourself, and finally I think you will remember everything. So until now, I still don't remember all of them. I just try to remember some specific unit for the mass and specific unit for the length. That's all. So when we have the quiz, even though you don't remember, but you can recalculate by yourself. And then you will figure out maybe your answer has some difference compared to the table. But no matters. It's just some constant value you change the difference accuracy. Okay. So I emphasize again the unit conversion very important in this class. Even though you understand what the question's meanings, but if you cannot do the unit conversion, you cannot find the final answers for any exercise. So you should keep all the unit conversions here. And then in the following, we will have some practice for the exercise. And then you will see how important of the unit conversions. Okay, so that's the first try. We have the exercise associated with the unit conversions. So we already know the gamma equations defined by the density multiplied by 1 gravity. So the gamma, we call that is the specific weight. It's a very important parameter in fluid mechanism when we calculate the pressures caused by the liquid. Okay? So first, the answer already showing here. This is the gamma for the waters, and but with the different units. The first one, we know that this is the SI unit, or the metric unit. And the second one answer in here, we know that is the English unit or the imperial unit. So how can we compute the number showing here? Okay, so the first, we step by step, we know that the gamma is the specific weight defined by the law G. And we know that the density for the water under the room conditions may the 1000. And because this is the density, so the unit is the kilogram per meter cubic. And we should multiply the gravity, right? So the gravity is 9.81, and the unit is the meter per second square. And we should we know that the kg in here, and we have the meter per second square is the acceleration. So we know combine the 2 kg and the meter per second is the unit is Newton. So that's why finally we can rewrite our answer is 9810, and the unit right now is a Newton per meter cubic. Okay, but this answer is for the metric unit. So this is a metric unit. But I'm wondering to convert the unit to imperial unit right now. So if you remember, we know the 1 pound force will equal to 4.448 Newton, right? If you forgot, you can go back to C and check in here, okay? And then you know that. So if you want to convert the metric unit to imperial unit, you need to know 1 pound force converted to the Newton, how the relationship. Okay, and then the second we should know 1 ft. I wondering to convert the meters 0.3048 meter. Again, if you forgot, you can go back to check the table, and you can show there are some the answers showing here. So we only keep 2 important parameters here in mind, and then we can convert the unit very quickly. So right now we know that the 9A10, and we wondering to convert the Newton to LB force, okay, pound force. So we should initially this is Newton, so we convert. So we should divide it the 4.448, convert the Newton to FB force, LB force is a pound force first. So right now I convert the Newton to pound force, and the second I need to convert the meter cubit to the FT. So I convert the FT should be the 0.34048, but this is only 1 times. But right now we have the cubic meter here, okay? So we need to have the additional cubic powers for unit conversions. So it will be to the FT cubic over 1. Okay, so you can check by yourself, and for me I use my calculator to double check the answers. Okay, the final answers will equal to the 62.45 around. And the unit is the pound force divided the FT cubic. Okay, so nothing difficult here. Only one idea is you should know some important unit conversions. Again, for me, I only remember FT to meter and the kg to pound mass and the pound force to Newton. That's all. And you can convert any unit very quickly. Okay, so but I also emphasize, if you repeatedly recalculate every time, finally you will keep the number in mind. So you don't need to recalculate again. Okay, so this is just a simple exercise, and we help us to remember some important unit conversions. Okay. And then in the following slide, I'm trying to introduce some equation literacy. And the first one is Newton's law. Everything sit here know very well and are familiar with the Newton's law. The Newton's law of the universal gravitation here. So I just wondering to remind you the magnitude of the gravity force is equal to the 2 mass multiplied together and divided to the distance between 2 mass square. And we also actually know the gravity will equal to the Earth's mass divided the Earth's radius square and multiply the constant gravity. Okay, that's why we use the 9.81 in our gravity constants. Okay, so that's all. So my focus, the second equation is the ideal gas law. So as I mentioned, when we discuss the ideal gas, we just based on the information of the force between two molecules. So, but still have some conditions we should take in mind. Is I show some list. There are conditions are not satisfy the ideal gas. So you see the first one. The first one, when a gas is very cold or very high pressures, and then the molecules can move very close. As I mentioned, if you put two molecules very close, that will some impulsive force or attractive force. So that means there is an interaction force between two molecules, so we cannot satisfy the ideal gas. The second, if you have the two phases together in your systems, that the liquid and the gas phase are present, you may want to be careful about applying the ideal gas law. Because if we have the two material are present at the same systems, maybe there is some viscosity force or other interaction force between two phases. So in that way, you want to apply the ideal gas law will have some troubles. Okay? And the final one, if the gas is very hot. So in case we consider the rocket in the exhaust stream, and in that way, the gas may ionize or dissociate. Okay, so in that way, if very high, so we have a very high kinematic energy to move the molecules. So, and then the molecule will ionize or dissociate. And in that way, we cannot apply the ideal gas law. So not only discussion with the interaction force between two molecules to consider the ideal gas law is valid or invalid. There is some condition also will increase the interaction force between two molecules. So I just summarize: very cold or very high pressure or very hot, we cannot use the ideal gas law. And the middle reason in here is the two phases combined together in your systems. You should be careful. Okay. So right now we would like to know more details for the ideal gas law. And we always mentioned the molar mass in the previous slide. So we actually know the molar mass for the hydrogens, helium, carbon, nitrogens, oxygens, and the dry air. Most of the famous molar mass we will use in our life. So, but you can see some numbers are not the integers. There are some floating numbers like the 107. But usually I didn't remember. I just keep the integer part for the 1, 4, 12, 14, 16, and the 28.8. That's all. So, but the more important definition, what the molar mass, I always emphasize is the mass divided the molar numbers you have. So the molar mass is indicate the mass divided the molar number you have. So if we take a look this table, the table summarizes all formulas associated with the ideal gas law. So I can start from one famous. The famous one is PV is equal to nRT, right? In our senior or junior high school, we studied chemistry, and we know that the PV equal nRT, always like the we just try to remember the equation PV 等于 nRT. And then, but the difference is the RU in here, we call that is a universal gas constant. And this number, we remember it's the 8.314. And the important thing here is the unit. So I think most of the people sit here forgot the number or the unit of the gas constants. So in here, the gas constant, universal gas constant, the unit in here, you should keep in mind. The unit is the Joule divided the mole and multiply the Kelvin. Kelvin is the absolute temperature unit. Okay, and you may forget what is the Joule. The Joule is the energy unit, and usually we know that the Joule can be divided by the force. Maybe we have the force and multiply the length. So the unit should be F multiply the length. Like I put the I put the calculator and move the 10 meters. So how the energy is I need to provide. So the unit for the Joule should be the Newton multiply the meter. Okay, this is the Joule unit. Okay, so what I would like to emphasize the unit, because I'm trying to convert the different formula for the ideal gas law. So this is the first, we define the PV is equal to nRT. And the second, in here, I defined the specific gas constant. R is the specific gas constant. That means this gas constant is for the specific gas. Okay, so how can we compute the specific gas constant? It's R is equal to the universal gas constant divided the mass, the molar mass. So the molar mass will have the different numbers for the different type. Okay, and we know that the molar number will equal to the mass, right? Divided the mole. Okay, the mole number will equal to the mass divided the mole number. Okay, so we can convert first the universal RU will equal to the molar mass multiply R, right? Molar mass multiply the specific gas constant. And then we can put the molar mass in here, so we know that the mass divided N multiply specific gas constants. Okay, and then we can put the equation here back to the equation 1 here. So we know that the PV can be rewritten by the N, and I put the RU, replace the RU by the N, R, and also keep the absolute temperature here. Okay, so you can see some parameter can cancel out is the mole, and then we can rewrite the equations is equal to PV will equal to nRT. And then if we consider the densities of the parameter inside the equations, so we know that the equation 3 can rewrite it by the P is equal to N divided the volume and multiply the specific gas constant to the absolute temperature. And here we can replace by the density. So to be the low RT, to be the equation 4. Okay, and then this is just try to convert a different formula related to the ideal gas law. And I'm wondering to emphasize some important things is you can see the dimensional of the gas, specific gas constants is different compared to RU, right? Because the RU should be divided the molar mass in here, so we'll change it to the unit of the specific gas constant. So the Joule is the same, but the button is different. We have the Kelvin. Okay, we have the Kelvin, the same. But the difference is the kg here, but there is the molar. Okay, so you should keep in mind. If you forgot the unit, but you should keep in mind at least one. For me, I keep the RU, the unit here, so I can understand why the unit for R is this type. Or you forgot everything, but you should keep one of the equations showing here. Because you can make the dimensional balance. You know the pressure, you know the volume, you know the mass, you know the Kelvin absolute temperature. So you can convert what is the unit for universal gas constant, right? So you can keep the one equation you can remember in your mind. Okay, so for me, I didn't remember everything, but at least I will keep the one of my favorites, and I keep in mind. And in the future, if I use I apply the ideal gas law, I will pick out which one is the better for our exercise. Okay, so right now we have the another example for our exercise. So we look the question first. We know that the mole N is 3. So we have a 3 mole. And the material is the gas. And has the mass. We have the mass. It's 66 grams. Okay? And the questions, what is the specific gas constants for this gas? And please answer the questions by SI units. Okay, and I provide you the universal gas constant number in here. Okay, so if you remember the equations we already know is the specific gas constant will equal to the universal gas constant divided the molar mass. Okay, and then we know that the molar mass will equal to the M divided the N. Right? So right now, the questions we need to answer is what's the specific gas constant in here. And I double check what we already know. We didn't know the molar mass here, but we already know the mass and the molar number. So we can compute the molar mass first. And then we can directly compute the specific gas constant. Okay, so we can try to do. So the molar mass in here will equal to the 66 grams. Usually I will put the unit beside my numbers because I wondering to check the unit. And divided the 3 mole. Okay, so I know that is equal to the 22 gram per mole. And second, I would like to calculate the specific gas constant values. And I know that the RU in here is the 314. Maybe I just stop here. And then the unit is the Ch1, and divided the mole, and then multiply the absolute temperature unit is the Kelvin. And we should divide it the molar mass, right? So right now I divided the molar mass. It's 22. And the unit here is the G over mole. But right now a little tricky because the G is not for our SI unit. So we should convert the G to be the kilogram, kg. So right now we're wondering to convert the G to kg, so I can multiply the number here to be the 10 minus 3 to convert the G to kg. So the unit right now to be the kg. And we notice that the mole can cancel out. So use your calculator, you can compute the final answer. It's around 378. And why I always write down the unit beside my numbers showing slide? Because I would like to make the final dimensional balance. So we still have the J Ch1 divided, we have the kg unit in here, and we have the Kelvin absolute temperature unit. So this is our final answers. And that's why showing the table, the unit of the specific gas constant is the Ch1 divided the K multiplied the Kelvin. Okay, and as you can notice that I put another number here for the air. Air, the specific gas constant is the 287. So you can know the different gas will different molar mass. So you will have the different specific gas constants. And compared to the air, this number larger than air. Okay, so you will know the molar mass should be smaller than the air. That's the result will have the larger specific gas constants. Okay, so this is one exercise is very important. No, nothing difficult, but the important is we need to know the logical, and we need to know the dimensional, the unit, and then we can practice how to convert the different units to the different units defined. Okay. So it still have the following slide. So maybe we stop here and 10 minutes break, and we back the class to finish this chapter. Okay.